All right, so we were talking about the regolith. It really is just kind of a powdery substance, kind of like talc, like baby powder, basically. And it's the result of micrometeorites hitting the moon, hitting the rocks on the moon over and over to go over again for about 4 billion years or so. And we think that it might even be several tens of meters thick. Maybe something less than 100 meters thick, something like that. Um, all right. So on when we're talking about the thickness, I just paused the video. Sorry. The thickness of the crust is roughly 100 kilometers, um, and the crust is actually thinner on the side that faces the Earth. In fact, that's kind of why we think the Maria exist. Now, why would it be thinner on the side that faces the Earth? Um, and we think that it has to do with uh, it's probably related to the fact that the side that faces the Earth is undergoes a slightly greater gravitational force, and in fact, that's the entire reason for the tides, as you're going to see. All right, so on the far side of the moon, we don't really see that many Maria. There's maybe two of them that can be identified. Remember, the Maria are the darker regions. Um, so the crust, of course, is composed of silicate rocks that is very rich in aluminum and very poor in iron. Unlike the rocks on the Earth, which have they do have, the rocks on Earth, of course, have aluminum, but they're certainly not poor in iron. There's plenty of iron. All right. So yeah, this is just talking more about the mantle of the moon, which is probably olivine, very similar to the Earth's mantle. Um, it seems to be more rigid, and because the heat just doesn't have the moon doesn't have a lot of heat to offer to cause volcanic eruptions. Of course, remember that's always subject to change if we get more information, which the people will try to figure these things out. I mentioned earlier that there's that Chinese. Now, there might not ever be anything that comes of this. It might not be accurate, but right now the preliminary findings are from this Chinese um, lander on the. I think it landed on the far side of the moon. Is that the moon actually had volcanic activity? It possibly had volcanic activity just a few 100 million years ago, which would be pretty revolutionary um, in terms of our ideas about the moon. We don't think it has. I mean, originally we didn't think it had any lava, any volcanic activity for the last 3 billion years. All right, let's move on. So the core. Notice we have this very low average density, which tells us that there's not a whole lot of iron there. I mean, there's going to be some iron due to differentiation, but there's not a lot of it. It's certainly not, it's not an iron nickel rich core the way the Earth's is. There's no overall magnetic field for our moon. And what else? Um, this is some molten material may be below the mantle, and the again the core is very tiny compared to the core of the Earth. Again, the moon has no atmosphere whatsoever. It turns out that it's simply too small, so that if some molecules of a gas find themselves close to the surface of the moon, then what happens is when that part of the moon gets exposed to the sun, then those molecules will easily get enough thermal energy, enough heat from the sun to reach escape velocity. All right, that's the moon. It will never really hold an atmosphere for very long. It's not going to ever hold an atmosphere, but even if there's some gas that finds itself close to the surface of the moon, it's not going to be there for long. Okay, so one of the reasons is, of course, there doesn't seem to be any volcanic activity, so that there's a source of gravity, or a source of gas. There's no source of gas from because there's not volcanism. And then, of course, the fact that the moon's gravity isn't strong enough to hold onto gas molecules, or certainly, not when they're exposed to the heat of the sun. All right. We know the distance to the moon very, very well. We can actually bounce radar off of the moon. We've been able to do that since World War II, when radar technology came of its own. And so we know if you measure the round trip time to get to the moon, so that remember that there's not somebody on the moon saying, "Hey, the radar signal just got here." The radar goes, it comes back, so that's called the round trip time. If you just want to know the distance to the moon, you divide that by 2, and so this is just calculating. This is another way of it's the same calculation. You just the way I did it in class is I just take this 2 and divide the round trip time by 2. All right, so it's the same thing basically. Another thing, just to let you know, that this value, this is the average distance from the Earth to Moon. It's 300. It's actually closer to 384,400 kilometers. All right, and it takes the Moon 27.2 days to orbit the Earth, and that's based on what's called sidereal time, which is based on the stars. All right, so if you were to look at compare the moon to some distant star, and then see when the moon lines up with that star exactly again, it would be 27.3 days. All right. The other thing is we can actually send laser beams. Right. So now, okay. So let me just distinguish these two things. Radar is a longer wavelength, so that if you're using a longer wavelength, your accuracy is not as great as if you're using a shorter wavelength. All right. Laser beams use visible light, which has a shorter wavelength than radar, and so we can tell the distance to the moon using lasers much more accurately, right? I mean, we can tell where the moon is to within a fraction of a centimeter, or at any time. Now, so if you were to take a laser, like an average laser pointer is certainly not. It's not strong enough for that beam to make it to the moon and come back, right? I mean, some of the photons will make it to the moon, but they certainly won't come back. The other problem is if you did have a laser that was strong enough, when the energy reaches the moon, what happens is the moon just simply absorbs that energy. It doesn't bounce back, right? So how is it that we use laser beams? I mean, this slide says that we use laser beams, and we do. And the reason that we can use laser beams is because when the astronauts, there's the original astronauts that went up in the 60s and the 70s, there were 6 times, so there's 6 locations around the moon in different Maria on the moon, where we put down, or the astronauts, I should say, put down reflectors, little reflectors, and we know exactly where those reflectors are, right? Because we put them there. And so you shine the laser beam at the reflector, it'll bounce back. Again, if you just shined laser at the moon, that it's not going to hit. It's going to hit the regolith and not bounce back, right? Because the wavelength is too small. But if you fire it and you know exactly where the little mirrors are, that it'll bounce back, and that gives you a much more accurate distance to the moon. All right, so let's talk about synchronous rotation. All right, in this last little bit. So the moon, and our moon is not the only moon in the solar system that does this, by the way. So here's what our moon does. Let's say there's a little lunar mountain. Okay, so here's this little lunar mountain, off to the right hand side, and it turns out that as the moon of course rotates around on its axis, but it takes the exact same time to rotate around on its axis once that it takes for the moon to go all the way around the Earth. All right, so it's kind of like when you were a kid, if you ever played the game Ring Around the Rosie, where you hold on to, a bunch of kids hold hands and they go around each other, and they're going in a circle, but they're facing each other. So the near side of the moon, there's a near side and a far side of the moon. Again, both sides get light. The near side of the moon is always facing the Earth. All right. We get actually a little bit more than 50% that faces us, but the near side faces us. And so here's how it goes. So as the moon is rotating, right? So watch this mountain, right? So it's rotated 90 degrees, right? So think about it. It was pointing off to the left. The mountain's pointing off to the left. 90 degrees later, it's now pointing down the page. 180 degrees later, now it's pointing to the right. I'm talking about the mountain, with the direction that the mountain's pointing. But notice it's rotated. It's rotated 180 degrees, right? And then 270 degrees. The moon is rotated around 270 degrees. Now this little mountain is pointing up, and then it completes itself, right? And so now it's pointing again to the left, right? So that's called synchronous rotation. There are some moons. So this is actually more technically, this is called a 1-to-1 synchronous rotation. There are some moons in the outer parts of the solar system that orbit in. Oh, actually, Mercury, as a matter of fact, orbits the sun in I think it's if I remember correctly, it's a 3-2 rotation. So it spins. If I remember this right, I might not be remembering this right. I'd have to look out. It spins around on its axis 3 times for every 2 times that it orbits the sun. So so like our moon, it's a 1-1. So it spins around on its axis for every 1 time that it rotates. That every single time it orbits the Earth. All right. So and then there's other moons that are in these synchronous rotations. It has to do with when the moon is close to its host planet, and there's a tidal effect that causes this. All right. So we'll get more into the tidal effects. Now the moon's orbit is tilted with respect to the Earth. That's why we don't have eclipses every single month, and it's tilted by about 5 degrees. As you can see right here, it's tilted about 5 degrees with respect to the ecliptic. If you look at the Earth's equator, it's tilted greatly with respect to the Earth's equator. It varies between 18 degrees and 29 degrees, but with respect to the ecliptic, it's about 5 degrees. All right. And so that's why the moon doesn't line up with the sun all the time.